All right, guys, this is Parametrics Part 2. These are the application problems. So I am going to have you put your calculator, you need a calculator again, put your calculator in parametric mode. That's my dog's toenails on the floor. I apologize. All right, so mode, you need to be in degrees, not radians, and you need to be in parametric, okay? So make sure you're in degrees and parametric so that when you go to y equals, it looks like this, and your calculator should say degrees at the top. All right, I'm going to minimize that. We're going to talk about how to apply the stuff we've been learning to projectile motion. Predict. Well, apparently I can't spell. That's supposed to say predict its position. All right. Parametric equations are often used to simulate projectile motion. The path of a projectile launched at any degree other than 90 with the horizontal can be modeled by the following parametric equation. So in the past, we did like they threw the ball straight up in the air, but we can now model what happens when they throw it at an angle. So this is what it looks like on your notes, okay? And I'm going to go through and explain it here because it's a little bigger. It says for an object launched at an angle theta, so theta is the angle. We're going to put the angle in after sine and after cosine, and we're going to have to remember to close our parentheses around those. And then with an initial velocity v sub 0, so the problem is going to tell us an initial velocity. It's going to be t times the velocity times the cosine of the angle, t times the velocity times the sine of the angle. And then it says where g is a constant. Okay, so it's going to say minus 1/2 g t squared plus h sub 0, or the initial height. But we're going to make things easy. We are almost always going to work in feet per second. So instead of this negative 1/2 g, we're just going to use negative 16 t squared, which should sound just like we did when we did the initial, what Hofbauer called throw-up problems in the quadratics unit. Negative 16 t squared plus, instead of just, it was negative 16x squared plus v sub 0x plus h sub 0. Now there's going to be two components. There's going to be a force that's making it go horizontally and vertically, okay? If you were to do one that was in meters per second, then it would change here and you would put in 9.8, which would make this negative 4.9 t squared. All right, moving on. Here, this is what it would say if we had a reference sheet. It would say if it's in meters, you use this formula. All right, so here's an example. It says Kaylee's practicing free throws for an upcoming game. She releases the ball with a velocity of 24 feet per second. That is, okay, where's my pen? This would be v sub 0. At an angle of 53 degrees, this is going to be theta. And the horizontal distance from the free throw line to the rim is 13 feet. The vertical distance is 10. The front of the rim is 2 feet from the backboard. She releases a shot 4.7 feet from the ground. So this is h sub 0. And then we want to know, does she make it? So what's going to be really cool is we're going to be able to put this all in this equation, t times the initial velocity times the cosine of the angle, and then minus 16 t squared, and so forth in the y sub 0. And we're going to set our window up. This time we're going to use for t window, it's not going to tell us. And so t stands for time in these examples. So within 5 seconds, that ball is going to come down. If you put a too small of a window here, like you did 0 to 1 second, the ball will just stop in midair and you'll go, what's going on? All right, now, in regards to whether she makes this, she is, how far from the basket? 13 feet away. So when the x value is 13 feet, okay? Took 0.9 of a second to get there. But when the x value is 13 feet away, the ball is 9 feet up in the air. Well, how does that compare to this question? If the basket, let's see, the vertical distance is 10 feet off the ground. Well, by the time it hits the rim, the ball's only at 9 feet. Or by the time it gets far enough to reach the edge of the rim, it's only at 9 feet, so it's going to hit the net and fall to the ground. It is not a high enough shot. She doesn't make that one. All right, so we're going to apply this to this situation, and then I'll show you exactly how we can calculate those things. So Luigi is kicking a soccer ball. He kicks the ball with an initial velocity of 35 feet per second. That is our v sub 0. And the angle theta is 48 degrees. Make sure you put those two in the right spot. I've seen students get those backwards. So the x equation from your notes, let me see. The x equation, it says at the top of your notes, is t times v sub 0 times the cosine of the angle, and make sure you're in degree mode. And then the y equation at the top of your notes says use negative 16t squared plus t times v sub 0, which is 35, times this time the sine, because sine is y, right? Cosine is x when we were doing trig stuff. And sine of 48 degrees plus, the ball was 2 feet off the ground, so this is our initial height. So we're going to put a plus 2 on the back here. All right, let's type that in. Grabbing my calculator. This one was supposed to be t, which remember is the x button now. It will give us a t because we're in parametric mode. Then times 35 times the cosine of 48. And if we go down here, we have negative, make sure it's a negative 16t squared plus, and then it's the same thing but with a sign, so it's t 35 sine 48. You can put multiplication symbols in there, but it knows to multiply it all anyway. And then plus 2 feet on the back. All right, now again, your window, t is time. So I don't need negative time. And I'm just going to start with 1 because I want to show you what happens. I'm sure we're going to need more than 1 second for the ball to come down. This is x is horizontal distance away. How far do you think a soccer ball goes? I think more than 10 feet. I'm going to put in 50, and I'm not even sure that's going to be enough. Y is height. We don't need more negative height, but this might go more than 10 feet in the air, so I'm going to put a 20. And I'm going to graph it. I told you, if you don't put enough time in, it'll just stop in midair, okay? That's the position of the ball after 1 second. All right, so I'm going to go back to the window, and I am going to say, let's put in 3 seconds. Should be enough for it to come down. Now when I go to the graph, it actually does complete and hit the ground. All right, so before I go any further, in case you're stuck, my window was 0 to 3 by 0.1 and 0 to, I did 50 away. This is going across this way, up and down. I thought a height of 20 would be enough, and it turns out it was. So I'm going to do 2 things here. I'm going to quick put this slide down here for you. And then I'm going to go to graph and put a picture down here for you. But The most important thing is we're going to talk about how to use this question or this graph to answer the questions at the top. It says, how far will the ball travel horizontally? Horizontally is X before it hits the ground. So I'm going to go to the calculator and I'm going to trace forward until the height of the ball is 0, or as close as I can make it. By the way, if you go second trace, you can't calculate a value at a particular y value. You can't find a 0. These are all notations you will use in calculus. Cool, but not going to help us. All right, so as close as I can get y to 0, then the distance away from me is almost 40 feet. And it took 1.7 seconds till it got there. Now, you can, like here, it's getting close to hitting the ground. Here, it's just below the ground. The only thing you're allowed to adjust is if you wanted to try to get this closer to 0, you could adjust this value of t. So I could type trace 1.69. Okay, there it's just above. 1.695. I'm getting closer and closer to 0. 1.7 was just below the ground, close enough, okay? So we're about 39.8 or 40 feet away from us. I'm going to turn to the next slide here because I think I have that question. All right, at about 1.7, the horizontal position of the ball was about 39.8 feet away before it hits the ground. And remember, that was when we made y as close to 0 as we could. All right, so it could have also asked, how high did the ball get? So if we went back here, we could trace here. We want to know what the highest y value was. Looks to me like about 12.6 feet in the air. Now it says, will a defender 6 feet tall, 6-foot tall defender standing 35 feet away, would the ball clear the defender or not? Or would it? What would happen? So 35 feet away, so I need to go until the x value, is 35. Right there is about 35 feet away. And if the defender was standing there was 6 feet tall, the ball might hit him in the face, right? Because the ball is 5 feet up. Might hit his face or his chest. But it will not clear over his head. Will it clear? No, ball is 5 feet up. Okay? So that's how we're going to use this, and I'm going to do a few more examples. All right, Julie's throwing a ball at an initial velocity of 28, and theta is an angle of 56 degrees with the horizon from a height of 4 feet. How far away will the ball land? So we want how far away? We want an x value. Will it land? That means when y is 0. All right, and how much time will it take until the ball lands? Means we want the t value at that same spot. All right, so I'm going to put in my x equals t times 28 cosine of 56. And my y is negative 16t squared plus t times 28 sine of 56. Plus 4. And for my window, I'm thinking it's going to come down in a few seconds. I'll try 4 to start with. It's going to go away from me. My x is how far away does it land? I don't know. I'll try 50. It might need to be changed. And how high up does it go? I might do this 1 to 50 this time too, and we can change those if we need to. All right, so calculator. Y equals, this time it was 28t, don't forget the t, then 28 cosine of 56, and negative 16t squared plus t times 28 sine of 56, and it was 4 feet up in the air this time. I'm going to go ahead and put that on the screen. If you're having trouble getting these to work, you can compare your screen. All right, let me change my window a little bit. Might take a little longer. I could leave it at 3. I'll change it to 4 seconds, whatever. And I said I was going to change this one 0 to 50 and 0 to 50. All right, let's see if it works. Oh, I didn't need 50 either direction. All right, I'm going to quick change this window a little bit so it's clearer. I hope 20 is enough in either direction. Oh, of course not. Hawk power. X needed to be more like 40. All right. So there's my picture. How far away will the ball land? I want to get it to a height of 0. So if I trace, I want to get the y value as close to 0 as I can. That's probably as close as I'm going to get. It's not quite to 0 yet, so I could try if I wanted to type like 1.61. There, it hit the ground, okay? But you can just leave it at 1.6. It's really okay. So it's really close to the ground at 1.6 seconds, and it's 23.7 feet away from us. So it was 1.6 or 1.7. I can't remember anything that long. 1.6 seconds. And I think it said 23.7 feet away. All right, that answers both questions. I have a couple more examples. Jerome hit a tennis ball at a velocity of 38, initial angle of 42, from a height of 1.5. How far away will the ball land if it is not hit by his opponent? What is the approximate height of the ball at the net? So when the ball gets 20 feet away from where he was, what's the height at the net? So does it clear the net? All right, real quick, it's 30, oh, I forgot the t. T times 38 cosine of 42, and negative 16t squared plus t times 38 sine of 42, and it was 1.5 feet off the ground. 38 and 42. And this one is 38 and 42. And a height of 1.5. I'm just going to leave my window for now. If I try the window, it does go further away. So I'm going to change this to maybe 55 since I was touching the 5. There we go. That works. Okay. So here's my window one more time. If you're trying to duplicate this, I can put it on the notes. There's the window I used. And just in case you're having trouble, there's what I typed in. All right, so the question was, how far away will the ball land? So if I go here and trace, I want to get the height, the y value as close to 0 as I can. So I could use here, I might even do a little fancy 1.65 seconds in, That's pretty close to 0, 1.64. I'm just being all fancy. Either answer is fine. So somewhere in there, it's close to 0, and it's about 46 feet away. If I traced around here, it was 45 feet. When it's underneath the ground here, it's 48 feet, which means it would have hit the ground somewhere in there. So what did we decide on? I forgot. Around 46 feet. All right. And if he was standing 20 feet away from the net, okay. So now at an X value of 20 feet, so when he was 20 feet away, so when the ball got about 20 feet away from him, somewhere in here, it had a height of 11 feet. So it definitely cleared the net, okay? So at about 20 feet away, it was about 11 feet up in the air. So what is the height of the ball at the net? Around 11 feet. All right, one more. This is 80 and 80, so 80 degrees and 80 feet, so that'll make easy. X equals t times 80 times cosine of 80, and y equals negative 16t squared plus 80, oops, I almost forgot the t again, sine of 80. It's from the ground, so the initial height is 0. And I'm thinking our window, because it's 80 feet per second, our window is going to have to be a lot bigger. So 80 and 80 and 80 and 80 and 0. See, if I graph it right now, whoop, goes way higher than that. May even take more than 4 seconds to come down. I guess we can change that afterwards. I'm going to assume it goes pretty far away. I'm going to put 200. And I think the height might be even more than that. I don't know. I'll try 300, see what happens. Oh my goodness. Okay, didn't need that big of numbers on either end, but it's stopping in midair because I don't have my t value far enough. I'll put 6 seconds. Let's see. This looked like we could cut it in half. And this looked like we could cut it even more than half, probably. Let's see if that works. Nope, of course not Hofbauer. Okay, so random number there. Okay, there we go. Trace. All right, how long will it take to travel 10 feet horizontally? So I want to trace forward in time and tell my X value horizontally is about 10. So somewhere about 0.7, maybe 0.75, if I just want to guess. It's about 10 feet away. Horizontally is X. What will be its vertical distance at this point? 50 feet up in the air. What is the maximum height reached? So if I keep tracing until I get around this maximum up here, I'm looking for the maximum Y value, 96.9, almost 97 feet. So I would say about 97 feet is the maximum. How far away does it land? So the Y value or height needs to be as close to 0 as we can make it. Pretty close here. If we wanted to make this 4.93, I don't know, I'm just guessing. Okay, now it's underground. 4.91. You could just say the answer was at the 4.9. It doesn't matter. Somewhere. It's still 1 feet off the ground here. So anyway, but what was the question? How far away does it land? So we want the X value. When we get this close to 0, I'm just going to go back and trace. So we could say 68 feet away, 69 feet away, somewhere in there, a little over 68 feet. All right, I hope you liked these applications. I am going to skip this problem. This one would be in meters per second, but I don't think we did meters per second on the homework. If you did this one, you would use T 56 cosine of 12, and for y you would use negative 4.9 t squared plus T 56 sine of 12 plus 0. And then how far away would it land, and adjust your window and everything. I can put the answer on the notes if someone wants to try that one, but otherwise you need to do the few practice problems on applications. Thanks, guys.